Okay, our last example. So I hope by now you realize with every added resistor, the table gets bigger, it takes more space to fully complete, it takes more time, and I hope you're not getting intimidated. The more practice you do, the better you will get at this. I find that these problems, once you practice a lot, are kind of satisfying, kind of like a Sudoku puzzle where you're given some numbers and you have to figure out, based on the givens, what numbers are missing. So this one is the most challenging, not only because it has been given, it's the largest number of resistors, but also, unlike the other examples, we're not given all the resistances to always start with equivalent resistance. So that was something that had been a pattern. The way that we solve these problems differs from circuit to circuit and based on what's given. So based on what's given and the circuit connections. So you can never really just strictly follow what you did previously. So it's true problem solving. And that might be a little bit intimidating, but really satisfying when you solve it. So let's take a look at this problem. This one, is it parallel or series? So hopefully you realize it's a complex circuit because it contains both. It's actually a series connection between 2 and 3. And then 2 and 3 are in parallel with 4. And then that parallel section is in series with 1 and the battery. So this is a series within a parallel within a series. If we were to write out the equivalent resistance formula for this one, this spot right here, it actually would be a few steps and kind of complicated. So maybe it's a good thing that we don't have to worry about doing that first. There are easier entries into this problem. So if you take a look, we can fill in this using Ohm's law. So you could use VIR for resistor 3. So that might be your preferred way to start. And I hope you're completing these examples as we go through them, or maybe before or after, to actually try and see. There's other options other than Ohm's law to start. So pause this video. Do you see what are all the possible ways that you could start this problem? So maybe you're going to observe that right here, the current does not split going from the source into R1. And we're given I1. So that means that we know I source. So I'm going to start there. Why not? KCL tells us that during that, along that path, there is no split. Therefore, I source equals I1. So that's all you have to write. You could write 0.5. Oh yes, we should take a look at significant figures. In the original problem, we were given 2 significant figures. So we're going to actually report that as 0.50. Okay, so we could have started from Ohm's law. We could have started from where I did start. You could have also started from over here, knowing that the voltage across the parallel branches is the same. In this case, it's not V2 equals V4. It's V2 plus V3 equals V4. And that comes from KVL. So I think that's probably my second, choice. And if you're wondering where does that come from, well, V source equals V1 plus V4 if the electrons take this path. V source also equals V1 plus V2 plus V3. And if these two statements are both true, then V4 equals V2 plus V3. So we can just shortcut to say V4 equals V2 plus V3. As long as you write KVL, you don't have to write it all out. You can just shortcut to the actual statement. We have V4, we have V3. We're solving for V2. So V2 equals V4 minus V3. 5 minus 2.5 equals 2.5. Did I really have to use my calculator for that? No. Did I realize that? No. It is a coincidence that these voltages are the same. The voltage drop does not have to be the same. It's a coincidence, or we'll see later, it's because the resistors are the same. So remember, the voltage drop is like how much energy is lost across it. So if if current is the same, a certain constant resistance from one to the other is going to result in a constant energy drop from one to the other. Okay, so now we filled in 2. Pause this video to see if you can see any other places where we can move. You might say, well, we're already talking about KVL and looking at electron path. So why don't we just continue doing that to fill out the final V1? So we're going to use KVL to solve for V1. So if we go back to either of these statements, probably the first one is the simplest. We can do V1 equals Vs minus V4. Vs, as in the voltage gain across the power source, is 12 volts. Subtract, if the electron chooses that path, some of that 12 volts is dropped at V4, which is 5 volts, and then there's 7 volts left that would have to be dropped off at V1. So we've got 7.0 volts for that one there. As the problems get more complicated, you have to have a wider range of colors. Okay, so now what is a good step? So we look horizontally, we have some options for Ohm's law. So let's take advantage of that, since Ohm's law is pretty easy. So Ohm's law to solve for, how many things can we solve right now? We can solve for RS and R1, or I guess it's equivalent resistance. There's no resistance through the battery. The battery is the opposite of resistance because you gain voltage. But anyways, yeah, I think you know what I mean. R total, you can call it. So if V equals IR, R is equal to V over I, which is equal to 12 over 0.5. So 12 volts. 12 volts over 5 amps, which is 24 ohms. So we've got 24 ohms. So satisfying. And then R1 is V1 over I1, which is 7 volts over 0.5 amps, which is 14 ohms. 14. And then we can also use Ohm's law to solve for I3. Now, if we know current through I3, we'll find current through I2 because they're the same. So V equals IR. So you don't have to write V equals IR every single time you apply Ohm's law, but if you have, so for here, I was rearranging it in the exact same way. I didn't have to write it in the original, but here I'm just going to go back to the original because I don't want to make a mistake for calculating I3. So I3 is equal to V3 over R3, which is 2.5 volts divided by 10 ohms, which is 0.25. Hopefully you didn't have to use the calculator for that. So we've got 0.25. Okay, yes, this problem takes a long time, but yes, it is really worth it to practice these longer problems. Okay, so now we said if we know the current through 3, we know the current through 2 because there is no split. So the next thing I'm going to do is say KCL to solve for I2, and I'm going to use it to solve for I4. But I2 is a series statement. I4 is going to be like a junction, like a parallel. We're going to apply something for parallel. So here we've just got I2 is equal to the same as I3. So I2 is equal to I3 because they are in series with each other, which is equal to, or sorry, I2 is equal to I3. Sorry, that's a 3. This marker is getting fatter as it's used. I2 equals I3, which is 0.25 amps. For the other one, for I4, so we have to take a look at this point right here, that junction. So 0.5 amps is going in, and 0.25 amps is going out. So there's a split there. You have 0.5 going in, 0.5 amps going in, and then you have 0.25 amps going one direction. Well, what's the other direction? I4 is equal to I1 minus I2, which is 0.25 amps. 0.25 amps. So our final step is to use Ohm's law. You could use the equivalent resistance formula, but it would be pretty ugly. So I suggest using Ohm's law here because we have 2 out of the 3 things in the rows. So I'm just gonna slide over, and this would be step 6, Ohm's law to solve R2 and R4. V equals IR, R equals V over I. So to find R2, it's V2 over I2, 2.5 volts over 0.25 amps, giving us 10 ohms. Now, careful here. For 2 sig figs, we'd have to report it in scientific notation. R3 equals V3 over I3. So that's 5 volts divided by 0.25 amps equals, is that 20 ohms? So we're not going to round those there if they were rounded numbers. Putting them in, 1.0 times 10 to the 1 is how you show 2 significant figures. 2.0 times 10 to the 1. So overall, checking this, you could write this massive R equivalent statement and do it on your calculator and check. So I will just show you that. You don't have to do the double check, but you're more likely to get perfect if you've mastered doing your double checks. So I recommend that you practice doing it. So we've got different levels, like different layers that we have to unpack. We have to have an equivalent resistance for R23, then the equivalent resistance for the parallel circuit, then the equivalent, then add that to the equivalent or the resistance for 1. So our total, if you want to call it that, is equal to R1 plus, it's going to be the inverse of something. So it's going to be 1 over R2 plus R3 plus 1 over R4. So if we sub that in, 14 ohms plus 1 over 10 plus 10 is 20. And then R4 is 20. So 1 divided by 20 plus 1 divided by 20 which is 10, plus 14, is 24. Excellent. So we had 14 ohms plus this gave us 10 ohms. So our answer was 24 ohms, and we did find 24 ohms through another route. So in these problems, there are lots of steps. There are multiple ways, multiple combinations of steps in order to solve them. So you want to get comfortable with not insisting that there's just one right way to solve these problems. You want to practice a lot of different connections and a lot of different combinations of given so that you really are comfortable with these circuit analysis problems, even for something as complex as this.